Hey there, welcome to Calculus. Today we are going to be continuing to talk about strategies for evaluating difficult to solve limits. If you recall, in our last video, we talked about rationalizing and factoring fractions so that we can simplify them down to something other than 0 over 0. Because if you recall, 0 over 0 is an indeterminate form, which means if something simplifies down to 0 over 0, that doesn't really tell you anything. Today, we are going to be talking about Pythagorean identities. And these are relations between trig functions that might not be obvious, that you probably learned in your pre-calculus class, but that you might not have spent very much time on, or you might have some trouble remembering. So it's helpful to review them. First, I want to move to a different tab so you can see all three basic Pythagorean identities. So take some time, pause the video, write these down. Make sure that you know them. All right, I hope that you wrote down these identities and that you have a pretty good feel for them. You can keep that note on hand as we work through our examples today. So, for the first example, I'm going to write out a few examples, and we're going to work through them one by one. All right, I have written out your three examples. Pause and solve this first one at the top. The limit of 2 sine squared of theta over the quantity 1 cosine of theta as theta approaches 0. All right, I hope you paused and worked out the problem. I'm now going to work it out myself so you can see how I did it, and hopefully we got the same answer. Well, the first thing I would do is check, what if I just plug 0 directly in? Well, 2 sine squared of theta of 0 over 1 cosine of 0, 1 minus the cosine of 0, is what we'd be left with. And think back to your unit circle. Cosine of 0 is 1, so 1 minus 1 is going to be 0, so 0 on the bottom. And then 2 sine squared of theta, that's going to be 2 times the sine of 0 squared. And if you think back to your unit circle, the sine of 0, I apologize for the traffic. The sine of 0 is 0. So that means we're left with our indeterminate form, 0 over 0. This means we have to employ some strategy in solving this limit. So go to your angle identities and see if any of this can be subbed around. The one that I notice is that this is the same as 2 times 1 minus cosine squared of theta. And the limit, you should still be writing the limit over here. I am not, because I'm being a little bit lazy with my notation. In your notes, you can be, but on exams, especially free response questions on exams, you should be very correct with your notation all the way through to ensure that you can't be docked points for incorrect notation. Anyways, back to the problem at hand. The denominator is going to stay the same, 1 minus the cosine of theta. And go back to factoring our video from yesterday. You see some difference of squares right here in the top. So that means we can break this apart even further. And if you don't remember difference of squares, go back to yesterday's video where I wrote out the formula. So we will be left with 2 times the quantity 1 minus cosine times the quantity 1 plus cosine theta. All of that over 1 minus the cosine of theta. Then, of course, you will notice that these two parts cancel with each other. And then we can foil, or not foil, but we can distribute this 2 back across everything else, leaving us with 2 plus 2 times cosine theta. Then you can plug in 0 for theta, and remember that the cosine of 0 is 1, which means that 2 plus 2 times 1 will give you 4. So our answer for this problem is 4. Let's go over to Desmos and see if that checks out. So I'm just going to write in this first function and estimate what the value would looks like it is at 0. And I'm replacing the theta with x because Desmos will not let you type in theta as your variable unless you do it as a polar function, which we are not covering right now. But replacing your theta with x will not change anything. Oops, I forgot to type in this 2 up here. And you will notice that it does graphically seem like the limit is 4, which means we got the correct answer. Now, let's try this next example right here. The limit of 1 minus secant x all over the tangent squared of x as x approaches 0. Pause and try and solve it for yourself. All right, I'm now going to work it out myself so we can see if we got the same answer. So, again, first thing to do, plug in 0. So, the secant of 0 is the same as 1 over the cosine of 0. And remember, the cosine of 0, like we just talked about, is 1. So 1 minus 1 over 1 is 0. Then the tangent of 0 squared at 0, your sine is 0 over 1, and that squares to be equal to 0 over 1, which is 0. So we are left with our indeterminate form, 0 over 0. That means we have to employ a different strategy to solve this limit. Sorry about that cut. I just found that this does have our indeterminate form. So let's see what Pythagorean identity tangent squared is. So you go over to our chart, we'll see that that is secant squared of theta minus 1. And that's just some algebraic rearranging of this middle equation. So I'm still an eraser, whoopsie. That'll leave us with our numerator is going to stay the same, 1 minus secant x and then our denominator is going to be secant squared of x. I don't know what I'm trying to do right here. My handwriting is just awful today. Secant squared x minus 1. And I can already tell from the order that things are in that we're going to get a little bit flip-flopped around. So I'm going to rearrange the top part, the numerator of this fraction, a little bit before I do the difference of squares with the bottom part. So you can rewrite this as negative secant x plus 1, of course, and then if you factor out a negative sign from that, then you are left with negative secant x minus 1. And that's just, I flipped this around and then factored out -1. And then this will be written as secant of x minus 1 times the secant of x plus 1. And then these two parts will cancel, leaving us with -1 over secant x plus 1. Now, remember, if we go back, we already found that the secant of x is 1. So we are going to be left with -1 over the quantity 1 plus 1, or -1/2. And we can go check our answer graphically. So if we just move over here and type in our original expression, 1 minus secant x over the tangent squared of x, we can zoom in and see that it does appear to pass through -0.5, meaning our answer is correct. All right, now I want you to solve this final example. So the first thing I would do is evaluate the top part at x equals 0. Well, cosecant squared of x is the same as sine squared of x to the -1. And that's the same as 1 over the sine squared of x. So sine squared of x is 0 because 0 squared is 0. So that's 1 over 0, which is undefined, which means we don't know anything about this because we have undefined in the numerator. So let's do some simplification. 1 minus cosecant squared of x isn't quite a Pythagorean identity because cotangent squared of theta equals cosecant squared minus 1. And we have sort of the opposite. But we can do like we did above and factor out a negative sign to reverse the order of the terms being subtracted. So that will leave us with cosecant squared of x minus 1 over the cotangent squared of x. And now that we have this in a form we can work with really, really easily, we can rewrite this as negative cotangent squared of x over cotangent squared of x. And that is because of our Pythagorean identities. And then, pretty obviously, this will cancel, leaving us with just -1. And what is the limit of -1 as x approaches 0? Well, -1 equals -1 equals -1. So our answer is going to be -1. Now, let's move over to Desmos and check that. We have our original function written up here, and if you look at the graph, it does pass through -1, it looks like, at 0, which means our answer is correct. I hope that you found this video helpful. Tomorrow, we will talk about double angle identities. And I hope that you will join me and continue with me on this journey through calculus. This is Quillen signing